come to Heckle, haven't you?
You need a whistle.
No,
I've heard that you're going to need a whistle.
no.
They're
I can
expecting
shout.
blood. They're expecting bloodshed. I better sit here as
I'm
a boss.
expecting what?
They're expecting bloodshed.
Okay, good.
Test, 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 test. Test, prova, test. Test, prova, test. Test, prova, prova.
Is this one okay as well? Yeah. Okay. I see we've got a few more people coming in from the back, so just wait another couple of seconds. Okay, good afternoon, ladies and gentlemen. My name is John Dyer from Terrana, and I'm introducing the session on packet versus switching, circuit switching. It says here in the book that there's going to be a discussion about the superiority of packet switching over circuit switching. That's what it says here, okay? Don't shoot the messenger. So there's no bias or anything, right? Now, the session this afternoon is going to be, we've got two formal presentations. We have Ronald van der Pol from Sara, who's going to talk about Lightbars. And then we have Simon Lennon from Switch, who's going to talk about myths and legends and things like that. Then two of the panelists, those will be 20-minute presentations each. There'll then be two 10-minute presentations by the panelists. So Mauro Campanella from GAR and Kees de Laat from UVA. So with that, I will hand over to Ronald.
Thank you very much. Can everybody hear me so, like this? Yeah, I think this is the most easiest. My talk is about Lightbar support at the edges, so the campus networks and the enterprise networks. I will first give a brief overview of hybrid networks and Lightbars, and then what you need to do inter-domain Lightbars setup. And I will finish my talk with the Lightbar support at the edges. So what are hybrid networks? Hybrid networks offer both packet-switched services like the normal internet, what we are all using today. And besides that, it also offers circuit switch traffic. So as far as hybrid networks are concerned, there is no either or. It's both packet switched and circuit switched. And let the users, the customers, decide what they want to use. Many NRENs have acquired their own dark fiber networks. And this enables them, by putting DWDM and SDH technology to lit these dark fibers, this enables them to offer both these services. For example, on a WDM link, you typically have dozens of wavelengths, and one of those wavelengths you can dedicate to one user group or one project. And this project has full availability of that one wavelength. And the same thing you can do on SDH circuits. You can give a couple of time slots to a certain project. And these circuits, the wavelength circuits and the SDH circuits, these are called Lightbars. So what are the reasons that NRINs are going to deploy hybrid networks? There are some specific applications that have some quality of service demands, for example, high bandwidth or especially low jitter. And these applications cannot be run on the normal routed internet or have bad performance over the normal routed internet. And currently it's only a few applications that really need this service. And well, maybe, well, okay, I will talk about it later. Two examples are the Large Hadron Collider optical private network of CERN. CERN generates a lot of data, and this data is stored, distributed over a dozen or so sites around, mainly around Europe, but also in Asia and Northern America. And this is terabytes of traffic per year. Another example is radio astronomy, VLBI. And here the jitter is especially important. The signals of all the radio telescopes are sent to one place where they are correlated with each other. And this is why Lightbars, this is where Lightbars come into play. And also Lightbars makes it easier to do these kinds of private networks. So the Lightbars are layer 1 or layer 2 connection-oriented circuits. Either a complete wavelength or some time slots on a TDM layer. Traditionally, currently, many service providers do this with IP and MPLS. But if it is only the circuits that are important, then it's usually easier to do this with so-called Lightbars. And well, in my opinion, it's not much more than what we used to call least circuits. So at the left is an example of how MPLS works. It's always IP as convergence layer, because the service providers have an IP network and they put MPLS on top of it to provide VPN services. And the right part, this one, this is how typically Lightpath looks like. Either a SDH time circuit Lightpath or only a wavelength type Lightpath. And of course there's also a lot of work going on here to get rid of, for example, SDH layers. But it's a different philosophy. You still use the IP as a convergence layer. And of course, in the right part, the Lightpath example, you also would use IP on top of it, but not to provide the circuit. Currently, the Lightbars are mainly offered within one domain, because that's easy, and in that way the service providers, the NRINs, can offer these services today to their customers. They can offer VPN or optical private networks with these services, with these Lightbars. Research has started to do this automatically, setup of Lightbars, and also interdomain. And the interdomain is challenge. A couple of projects are looking into that. The Joint Research Activity 3, the Lucifer project, Dragon. And they are looking at the services to offer for tomorrow. And when you are looking at the automatic setup of Lightbars, the idea is that in the end, end users can set up Lightbars end-to-end, and then you need interaction between the different NRANs, but also between the NRAN and the campus or enterprise LAN. A traditional network as we have it today has the control traffic and data traffic both on the same link between the routers and switches. In hybrid networks, this is usually split into two planes or two parts. The data plane, where the real traffic flows between the routers and switches, and the control plane where the signaling and routing takes place. In IP networks, the OSPF or ISIS, BGP, things like that, run on the same link as the data traffic. In hybrid networks, this is separated between two different links. So the control elements are linked by a control network, and the data traffic is flowing between the routers and the switches. There are several Lightpath technologies being investigated. These three are the main ones: GMPLS, generalized MPLS, an extension on MPLS, user controlled Lightpath, and DUREC. DUREC is a Notel proprietary protocol, but it's also used quite a bit. Each has its specific use, and you see that each NRAN picks his favorite one. And in my opinion, there's not a clear architecture yet. There's talk about control planes, like I showed in the previous picture, but also the management plane, service plane, and all kinds of other planes. And it's getting pretty complex at the moment, and I think a more KISS approach is needed. And in my opinion, it doesn't have to be 100% perfect, but good enough to be workable. This is a picture that shows this a little bit. On the bottom, there's again the routers and switches with the data traffic flowing around. And this is called the data plane. And well, I've called this not the data plane, control plane, management plane, service plane, whatever. And here you have, for one NRAN, using GMPLS, another one is using UCLP, another one is DUREC, and you need some kind of interaction between those, and preferably some standardized way to exchange the information needed to set up Lightbars. And preferably standardized, so you have some kind of protocol X, so that DUREC can talk to UCLP, but DUREC can also talk to a GMPLS-based Lightbars setup. Then, of course, on the left you have the local area network. That's a different thing, Maybe you, on this interface, you talk the same protocol as between the NRANs, but maybe you can use a more simple protocol. Of course, that's preferred for the enterprises and campuses. If there are those applications that really need, for example, low jitter, then these applications, these quality of service aspects need to be offered end-to-end. This means that the Lightpath, that its quality of service, has to be supported up to the applications. And this means that also the campus and enterprise networks need to support those Lightbars through the network to offer the same quality of service that this specific application needs. And this is not a trivial task because the enterprises are mainly, mostly Ethernet networks, simple Ethernet networks, and the managers of those networks want to keep those simple Ethernet networks. They don't want to introduce DWDM or time division SDH technology, and also they don't want to be bothered with all kinds of complex control planes. So there are two sides of a light path. One side is the application, the end user, that sets up this light path. For example, the user wants to use some kind of grid application. They pick a couple of sites where they can get some grid resources. For example, one site they get a computer cluster. At another site they use data storage, etc. And then they connect these grid resources with the network. And then they can start using the grid. At the other side, you have the providers of these grid resources, so the computer clusters, data storage, visualization equipment. And they have to decide how to access those or offer those resources to the users. And also for these specific quality of service applications, then they need to support some kind of quality of service through their LAN. And there's some interaction between the campus network and enterprise network and the NRN or service provider. So this end user is picking some kind of several grid resources and building an optical private network between those resources. And the application wants to get the most optimal topology. Sometimes this is a mesh, sometimes this is a tree structure or a ring structure, whatever. And this is something that the Starplane project of the University of Amsterdam in the Netherlands is looking at. There's a poster session outside about the Starplane project. This topology, when you want to set up this optical private network, you have to describe that network that you want in some kind of machine-readable format. And one example that could be used for that is the network description language. It's an RDF resource description format based language. It's a namespace on RDF, and RDF is based on XML. And here, this is also a poster session outside. This is also work from the University of Amsterdam. And you can get more information on this URL. And some practical applications of RDF on the bottom URL. This is an example of what you can do with NDL. You have some kind of device, router switch. You describe it, you give it a name, and you say what kind of interfaces it has. And these are just pointers to something like in the bottom. So the interface 6/1 is described over here. This is about the interface 6/1 of the Delft network element. And it says it's connected to a network element in Amsterdam on port 9/1. And so you can, in this way, you can build the topology by describing it in this way. What you can do, this is unfortunately not very visible, but when you have this NDL description, there are all kinds of tools being developed. One of them is to visualize such a description. And then you can automatically generate a topology picture of the network that is being described by NDL. So what needs to be investigated if Lightbars need to be supported in local area networks? There is this interaction between the local area and the NRN about the setup, the signaling and the routing of Lightbars. Inside the campus and enterprise, you have to do something to offer the quality of service that is needed. If you look at the grid provider side of the story, then you need to handle who can use what resource, and on both sides also who can use the Lightbars, who can set up Lightbars. And a final thing that's not trivial, the NRNs are just providing circuits, and they're pushing all the routing and addressing problems to the edges. So the local area networks, the campus networks and the enterprise networks need to handle that. They need to handle how to set up addressing, because it's just a layer 2 interconnection, and you have to decide what addresses to use and how to do the routing, etc., how to run IP over it. That's the last slide of my talk.
I prefer to go right on to the next presenter. We've got a panel discussion at the end, so we have 30 minutes. If you could ask your questions there. The next speaker is Simon Lynan. He's working at Switch, and he's going to talk about the myths of the cross-barriers between packet switching
and circuit switching. Cool. So apparently these are my slides. But I make these bigger. Okay. Hi everybody. As said, we wanted to make these slide presentations a little bit shorter so that we have more time for discussion for the panel afterwards. As John said, I work for Switch, which is the Swiss National Research and Education Network, which is one of these NRNs who have their own fiber networks. We've had ours since 2001 or 2000, I guess. Somebody correct me. But we have no light paths, and sometimes I feel bad about it because everybody keeps telling me you need these light paths. They're so nice and cheap and so on. But we have this opposite strategy, and we try to keep our customers happy with a stupid old IP network that doesn't have quality of service and so on. And we let our customers make these connections too, but it's even easier. They don't even have to ask them, us or any kind of control plane. They just do these connections between consenting endpoints using something like TCP or so. So we have connections, but we don't call them that. We just provide a packet service. And the idea is, of course, to make the packet service good enough so that the demand for these specialized connections, like light paths, remains low. And as a caveat, there are some things that make this easier for us than for many other networks, probably. For example, we don't have any radio telescopes in Switzerland. I think no one has discovered any yet. We do have these nuclear physicists at CERN, but somehow we have our own tricks to make them connect to the rest of the world without us having to provide light paths for them. It's, yeah, there's administrative procedures that allow them to do the patches themselves. Yeah. So one argument that is always brought up in favor of providing these light paths is it cannot be cost effective to build IP networks that are good enough for all these people, these high performance users. And, well, as I said, this is from a biased perspective. We have maybe less of these very demanding users, so this may not apply to everybody. But we look at some ingredients of the cost structures of building these networks. Okay, so what you often read in the introductory paragraphs of papers and presentations about Lightpath supporting networks are like these claims. So the bandwidth prices continue their free fall. So let's just consider bandwidth is free. Okay, fiber is just lying around in the ground. You can buy it cheaply from bankruptcy auctions or something, and then you can do DWDM and multiply this free bandwidth by large factors, and then it's even less than free. And but once you start routing is very expensive. Routers are expensive. Interfaces are especially expensive. From that, it follows that the only way to build these networks cost effectively is to use DWDM to provide infinite capacity, and then use like a little part of that, like one wavelength, or it's always pairs of wavelengths. By the way, this struck me in Ronald's presentations. A channel is a bidirectional channel is 2 wavelengths, right? So you set 2 wavelengths aside, and you use this for IP service, and you declare that as the legacy network, and everything else is like specially switched light paths. Okay, this is sort of the canonical way of building real NRANs today, and this is why we are not doing that. Okay, so first of all, bandwidth is not free, of course. Unfortunately, once you have a DWDM network, of course, adding another pair of wavelengths is relatively cheap. Okay, you just need like transponders at the edges, and you can use the same amplifiers, and hopefully you have some space in your optical multiplexing grids. So adding a lambda is free, more or less. But for that, of course, you have to do a really large upfront investment. You have to secure your fiber, which is usually long-term leases, and construction projects for local loops. Usually you have to construct some yourself. You have to buy and run amplifiers, and these things are not cheap, especially not cheap to operate. If you look at some of the stands that you have, you're supposed to buy like special management applications and pay people to run around, replace the stuff that breaks and so on. It's not free. Yeah, this covers both the investment and the running of the infrastructure. So what I see often is like what I call creative accounting, and I really think this is slightly unfair to the packet switching crowd. But what some people do is they say, well, we have to build these networks, and so. Well, as we said, the first wavelength is used for this legacy IP stuff. So let's say this has to pay for the entire upfront investment. And then we have these 3 wavelengths, okay, and we give them out at the marginal price, marginal cost, okay. Yeah, so you create demand for these things. Okay. The argument that we always hear against building fast routed networks, which is what I'm in favor of, if you haven't noticed that by then, is the line cards are so expensive. The line cards for high capacity interfaces. And that is true if you look at, so all the examples are in actual prices from a price list that has been found somewhere on the internet. I don't want to say what currency it is, and it's without discount. But look at the relative prices. It's really for the sake of an example. But these are actual prices for packet over SONET line cards at 10 gigabit per second, and you see these are really hefty investments. If you, I don't know, oh, you don't. But trust me, it's like in Switzerland you can build a small house from these. Not disclosing what kind of currency this is. So this is a 10 gig line card. You see, there are these line cards are expensive no matter what kind of router you buy to put them in. Carrier class routers are like what I call a glorified layer 3 switch, which is something that could be used as both a campus switch and a backbone router, which is the stuff we use for our network. So these line cards are really expensive. Then let's look at a couple of price examples in the 10 gigabit Ethernet space, and note that the capacity is slightly higher. Okay, a 10 gig E line card, ideally, I think these all run at line rate, so you can run them at 100% capacity. So these are like 10,000 megabits per second, and the Sonnet stuff does only 9,950 or something. So these are actually faster, and but they're less expensive. Especially when you look at this, the variant for the glorified layer 3 switch, you can get really low port costs, which is like, I don't know, more like my monthly salary or so, instead of a house for one port. Still not disclosing what currency this is. These line cards are actually modular. I think that's true for at least the two lower ones. So you need optical transceiver modules. Actually, you can also use electrical transceivers if you have local connections. And the cost examples for these modular optics or transceivers run from 600 to 20,000. But the 20,000 thing, it is a DWDM XenPak transceiver, so you can plug it directly into the passive parts of an optical infrastructure. So some of this cost is actually part of the optical transport domain. Okay, so it's like unclear whether you would want to put this into accounting for the router network or for the transport network. Okay, and the feature sets for my personal purposes, it's pretty much the same over all these routers. What I'm interested in is that they perform line rate forwarding of IPv4 and IPv6 traffic for both unicast and multicast. They also support MPLS, I think, and some tunneling mechanisms. And when I look at the same price list for components of optical network, I see that at least these last port costs, they compare quite favorably to just stupid transceivers that take one payload from like a neutral LAN interface and put it on the right wavelength for optical transport. So there's really not much to save here, if you have to do the regeneration anyway. Okay, so like if your network is big, so this is not at all. This doesn't apply to Roland's LAN case, but it does apply to many WANs where you have to regenerate the signal, and the regeneration span is like similar to the distance between your routers. Then you cannot really save much by leaving out the routers. Of course, you cannot just buy the line cards. They won't work without a box to put them in, which is, by the way, is also true for the optical systems. The optical shelves, I think they are cheaper. I haven't done my homework and looked at the exact prices. But for the chassis, we see a similar situation. The differences between the standard carrier class routers and the glorified layer 3 switches is even bigger. So you see that there is some truth to this assumption that routed networks are expensive when you consistently use carrier class routers. So don't do that. Okay, so there's a side discussion. Some people tell me, and yeah, of course that makes me mad, that the routers in my networks, they are not really routers, they are switches, okay, because they are like too cheap or something. So as a compromise, let's call them layer 3 switches. So for me, a layer 3 switch is like a router, okay, because it looks at the IP address, network layer address of the packets and forwards according to that. What else do you need for a router? They have to participate in the routing protocols, you know, this control plane, but these layer 3 switches can do that. They often have some restrictions. For example, ours don't, well, ours do IS, but we refrain from using that because we know other layer 3 switches don't, and maybe we want to downgrade sometime to another vendor. So you do have some restrictions. But it is not the fact that these boxes root that makes them like expensive. You have often these layer 3 switches have forwarding planes based on ternary cams, so TCAMs. It's a special sort of content addressable memory that has wildcards and that can be adapted for all kinds of routing, table lookup like things, including executing access lists in constant time and so on. So basically these boxes are cheap. One reason is that they are based on pretty generic hardware that's very fast and high volume, and they have limited possibilities to implement new forwarding schemes by programming these TCAM things intelligently. But you have to know the limitations of the hardware. And one thing that's nice about these things is that it is relatively cheap to replace just the forwarding hardware because we have centralized forwarding. So we only have to replace the main boards, which are cheap, and we don't have to replace the interface cards, which are expensive. Well, these are not so expensive, but of course one reason why the carrier class router line cards are expensive is that they have a distributed forwarding architecture, and on the line cards you have lots of forwarding intelligence or resources for very fast forwarding, which makes replacing these interfaces really annoyingly expensive. So again, looking at some aspects of cost for circuit switch versus packet switch networks. So the forwarding capacity or switching capacity is measured in gigabits per second or terabits per second. This is where the circuit switched networks really shine. I mean, an optical switch can be very simple and can be agnostic to the payloads transport, so you can upgrade it easily. But sometimes, if you have to support these end-to-end light paths, it can be difficult to upgrade parts of the network and still maintain the end-to-end service. I'm not sure about the number of endpoints you can connect to the network, how that scales. Haven't had the time to think about that. But of course, the number of connections that these networks can sustain is like infinite in IP networks because the connections are only between end hosts. Okay, the network doesn't care who connects to whom. That is very nice. And these DWDM networks, well, they all have limitations. They can get pretty impressive, the high numbers of wavelengths that they can support, but at some point the fiber is full and you have to buy new fibers and new boxes for the fibers and so on. Also, the connection setup rate, although theoretically a DWDM network with a suitably tuned and implemented control plane could be measured to set up connections like at light speed, more or less, but it will always be hard to sustain a high throughput. And for IP networks, this is all distributed to the endpoints, to the hosts. Okay, so the more hosts you have, the more capacity for connection, for making connections you have, and the network doesn't have to care. Also, for building resilient networks, packet switch networks have these, or at least if they look like the internet, there's no connection state in the network. So when stuff in the network fails, the endpoints have enough state to keep the connection alive as long as there's an alternate path. So a few tips if you want to build a fast and cheap rooted network. What makes routed networks expensive. So one, we've already seen that is carrier class equipment. This equipment, for example, it has internal redundancy, like 3 power supplies, 2 root processors that can fail over in picoseconds and so on. They are very scalable, hence the distributed forwarding. Every line card takes part in the forwarding. So they scale to like thousands of interfaces. In research networks, very few research networks actually need that many interfaces. Even if you look at Géant, the typical Géant router has what, like 4 or 5 neighbors, right? Not more. So the scalability is something you just waste money on most of the time. And the development costs for these things are impressive. I looked at the literature on Cisco's latest carrier class router. It was a $500 million development project, okay? Now the router has been out for 2 years. I found a press release from 6 months ago. So in the first 18 months, 100 boxes were sold. So, and like the typical price will be like 1 million. So you can imagine these are all subsidized by Cisco, and maybe probably in a few years they will make money for them. But it's not as easy. The development costs are a big part of the costs. Also, you should avoid complex feature sets, and it's better not to need bleeding edge performance. So on the technical side, we may discuss this. Large buffers in interfaces make line cards expensive. So do you really need them, or is it better to try to build a cheap network that you can always upgrade to so that no buffering is ever necessary? Large routing tables is something that really bothers me, really concerns me. Small routing tables seem to be okay. You just buy TCAMs or put them in routers. But large routing tables could be a big problem, would be a problem for us. So, as I said, try to use these glorified campus switches, layer 3 switches. They all support 10 gig E fine, and they will become even cheaper because these things are starting to replace like fiber channel systems, storage area networks, and backplane technologies. Like people are moving from fiber channel to 10 gig E, they're moving from I don't know, Hippie or what was MyRenet to 10 gig E, so this will all make these things cheaper. And the most difficult part is decide on the features that you really want to support. This is my favorite feature set. Yours may look different. We have to support IPv4 unicast, that's for sure. We also want to support IPv6, and we also want to support multicast. And we have to support, well, end-to-end Ethernet formed connections. And the way we do this right now, mostly, well, we also sometimes build special lambdas for customers by hand. But we usually use something called Ethernet over MPLS. I would prefer using Ethernet over IP, but current vendors don't support that. So this is a picture of a network. All the red dots are routers. That's the important part. No switches, no nothing, just routers. And well, this is our current topology. The thick links are 10 gig links. The thin link are 1 gig links. And well, unfortunately, I cannot tell you how much this costs, but that will be interesting. Mauro, you asked the question. These numbers are all confidential, I heard. So looking into the future, how can we ensure that future networks are fast and cheap and scale with our user demands? So I think an interesting research topic would be how can we achieve a good network quality of service without large buffers in the network. Okay, this is like common wisdom that in a backbone network you always have to provide at every interface like the maximum or typical round trip time, end-to-end round trip time, times the circuit capacity with a buffering, and that is expensive. And it's not just expensive, but when it is used, it also increases jitter. So it would be better to get away with small buffers. Maybe we need some edge solutions for these high demanding users. And well, I have this idea for a network that's even better than IP, that leaves all the path selection to the hosts. But I guess there's no time to go into that. So thank you for your attention. Thank you.
Was speaking, I was making some rough computation. I used the web. I was on one of the famous economical newspaper, and I looked at the gold value today, which is 24 euros per gram. So then I took the weight of one of those large routers interfaces, which is let's say 140,000 kilo euros. Sorry, 140,000 euros. Then I divided by its weight, which is roughly 7 kilograms, and I got exactly the same value. So be aware not to scratch your interfaces in your routers, because you may scratch few euros out of them. That's one thing. The second thing is that, unfortunately, in Italy, we both look at the sky and underground high-energy physics tunnels, so we have more needs. I thought it was useful to introduce the discussion, providing additional facts. And if you want, just to start, how can I start it? Okay. Okay. I decided to take the GAR network and show you some graphs and some private consideration on what's going on in the last months in the GAR network, and how this actually helps us in taking a good, let's say, short to medium term decision on the type of network. I don't want to be religious in what I discuss. I just want to have a look at what we need now according to the user's needs, which are the traffic needs, if you want. Okay. This is a plot that shows you in the last, let's say, 6 years, roughly, the growth of traffic in the backbone towards the general internet, not the research environment, just the general internet. The reason there are 4 colors is that one, the red and blue are the usual averages on a day. But I think it's much more useful, if you really want to understand what's happening in your network, to look at the peak in each day. So these 2 reddish and bluish color actually corresponds to the highest peak for each day, which is, in my opinion, much more important to understand how loaded is your links. I tried to take out some conclusions. The network is a pure packet switch and network, nothing else. It still keeps growing a factor of 2 per year. It's true. Being in Italy, we started from a very low level, but nonetheless, even in the last months, you can see the high increase in throughput. I particularly like the peak each day because it can show you also that it's not just the traffic that increases, as the burstiness that this is also increasing. And this is one thing that allows you much better to understand the need of sizing of your network. I will elaborate a little bit more in what means end-to-end highly dynamic random, in the sense that it's very difficult to predict where traffic will flow in the future unless we take an hypothesis. The quality, I think that Claudia can correct me, which is responsible for the backbone, but in practice, these, which is a pure packet switched network with decent routers, unfortunately not yet switches, has a very good uptime. So it works very well, the users are happy, and mainly we have no packet losses because obviously the core is slightly over-provisioned compared to the sum of the ingress. General internet, I'm sorry I wasn't able in the last days to catch all the data. What is important here is exactly the same thing, but it's much more bursty. So researcher looks much more active and try to use much more bandwidth-hungry applications than in general internet. The following plots I show you are based on a net flow analysis we did a few months ago with a student, just to show you that the net flow is valid, although you have a 1 to 100 sampling on packets. I show you two graphs. One is the standard SNMP based bits per second, bytes per second plot, and this is the one which came out from NetFlow with a 1 to 100 sampling. Apart from a factor of 100, they are exactly the same. So these gives me enough confidence to say that the following plots which I show you, and it will are based on a 1 to 100 sampling, are roughly correct. Okay? These has unpublished data, so not yet. But I think it was useful to show them. Flow size. If we want to do packet switching versus circuit switching, the fundamental thing is how long is one session? Because if it all is short and not very fast, well, the time to switch and create a circuit and essentially create a circuit-oriented connection is much longer than anything else. So what I discovered is that essentially still the majority of the flows are around 1,000 bytes. And then there is a fast decreasing slope, is a log-log plot. The same for the duration of the flow. A majority of the flows are around 10 seconds, which is a long time, I agree, but not so long. Okay, so this is the time scale we had to think about. If you think about circuits for flows, for a single flow, because I think this is one of the most important things. I'm trying to do one thing which is far from being easy, because we are all familiar with Gnutella, Kanza, which now are called eDonkey, eMule, and BitTorrent. But what that means in reality it means that if you take a single node and you plot the average of flows per node at the same time, which means with how many different endpoints a single node has a connection open at the same time, then you got that one. Yes, it's one of the most important thing, but it's not alone. You have relay slope, which means that an average node could have an average connection which is larger than one. So it's not true that you think in one-to-one connection any longer. According to the traffic of 6 months ago, which, as long as I can understand, is increasing now. So end-to-end have to be thought a little bit better. Now, expensive in money, I agree, gold-like things. How is expensive in manpower? Because the other side is that to run a network you need persons. What I wanted to show here is that we offer connectivity to large European projects. So we created this MABED testbed, which is actually layers 2 circuits using MPLS technology on all our NRNs. It was not difficult to set it up, but it turns out that it takes roughly about 4 months of an expert technicians a year to keep 4 LSPs up and running. I agree, this is not fully developed technology. Our technicians might be not fully expert in everything, but nonetheless, I gather from these that it's far from being trivial, it's time consuming, and at least half of that time is due to bug in the thick software layer in the MPLS, in the routers. So the more complex is the router, the more bugs you will find. Nothing strange, but that is what it means. So if you really want to use a very complex technology, which is, by the way, needed if you want to use and create virtual circuits, MPLS, GMPLS, I don't care what the name, then it means that you have to invest more money in human beings, expert ones. So, just 2 slides, personal conclusion. I think that we have to look back at history. There have been very good reasons to move from circuit switching to packet switching. So we have to keep that in mind. Keep also in mind that a packet switched network is so simple that it is easily upgradable. You can very easily add nodes, capacity, switches, whatever you want to a pure packet switched network in almost no time, which is well suited to the research network timing needs. So having a simple network allows also an easy and faster innovation, which is much more difficult if you have a completely circuit-oriented network. Standard traffic. Well, the traffic tells me that it's constantly growing. I had not the time to show you, but it's going everywhere. If you look at all graphs in all your networks, there is a flat, constant pedestal everywhere. To me, that means that the traffic is going from everyone to everyone, which means that there is no preferred directions. There is no preferred way to decide which is the best circuit to create. So it's much better suited to dynamic packet switching than to circuit switching, because it also dynamically changes very fast. Okay? I have personal feelings against clever networks. I don't like them, because I've seen since the old ATM times that the more clever the network tries to be, like Microsoft products, the worse it is for you. So I don't want cleverness in the tool I use. That was an easy joke, I know. 1 minute, fine. That's the last slide. End-to-end, let's remember that end-to-end really means scalability. And I do want to be scalable. And if you really want to be scalable, you have to have a simple network. I can't see any other possibility now according to our needs. But for sure, we need some improvements in transport protocols to allow higher capacity flows. I see some good reasons for that. So work is ongoing, but it's nothing to do with the network itself. TCP runs on end nodes. So a simpler network is much better suited for more complex end nodes. Grids, everyone says, well, for grids we need very high capacity point-to-point links. Yes, if a grid is made by the 7 tiers 1 of for CERN research. But what if it is made by 1 million of sensors attached to human beings or buses or cars? Then each sensors will produce low capacity, will need low capacity, but there will be a zillion of them. You can't do that with circuit switching. So the best solution, again, in my opinion, so it's a panel from now, is not to use the standard circuit switching for those sensors, which I believe will be the majority of them, but use, again, packet switching. Since I am, in any case, also a little bit of political thing on the political side, I hope that we'll try a correct compromise between the two technologies, because indeed a radio telescope will not move. So I think it's sensible to provide him a direct link using circuit switching. But for the rest, well, the debate is open. That's it.
I have a downhill battle, so I try to not go on the slippery slope as the previous two speakers. I couldn't upload my slides, because if I would have done so, I would have deleted the previous presentation. That's very interesting. So let me check. Turn on mirroring. So I guess I'm supposed to give you a view and defend a little bit where and when circuit-based or lambda switching lambda networking is and should be applied, because I think that is necessary. So this is a slide which I showed many times before. Started to show this slide about a few years ago, so I guess about half of this our audience has seen this slide. I also am sometimes at meetings where it's just the other way around. Half has not seen it. The idea is to look at the user base, and I divide the users of a network in 3 different classes. And at the x-axis you see the typical bandwidth requirements of those users, and vertically I estimate how many users use this kind of bandwidth and what the characteristics of those traffic patterns are. I don't say if this is log lin or linear log, I don't care about, it's more kind of trend. The A class for me are typically, you know, home users or users which use these short flows. So all the graphs, in my opinion, which Mauro showed, are actually basically class A users. It are users which do browsing or whatever you want, but every next flow can go to anywhere on the internet, and it is short to medium duration. And the speeds they typically need to do their work, like you all who are reading your email, is just, you know, ADSL speeds, and that's a moving target. I have now at home 8 or 12 megabit, depending if the ADSL provider got this business right. And so that is the majority of usage. And that also holds for everybody who considers himself here a high-end user reading email at his desk, including me. You don't need lambdas for that. Then there's this B class. These are more these, you know, applications which go client-server or inside confined environments, typical inside industries or institutes and so on, and you can get away most of it by using just layer 2 technology, what everybody is doing, so nothing new there. And those typical speeds today to the desktop are gigabit Ethernet. And if you look at those traffics, it may be longer lasting flows, but it is usually from several IP addresses to many or several IP addresses and uplink to internet. But then you have this very small yellow piece there at the end, and that are those applications, as you can see at IGRID, or the usual suspects currently are the high energy physics community with the tier 0, tier 1 flows which go there for years if they get their accelerator running. And the astronomers, for example, combining the EVLBI stuff, combining telescopes just to get better resolution in the sky in real time. And as I later will say, some new emerging applications. However, if you try to add up what we see in Holland, but mind you, I'm not running a network. I'm trying to run a research group. I'm not from SurfNet. SurfNet runs network. But if we look what requirements from Class A, Class B, and Class C users come to the network, they are approximately equal. The amount of bandwidth demanded for EVLBI is equal or surpasses what the Class A, the normal, let's put it that way, BitTorrent and so on from all the students together use. Then there is this observation which partly was actually supported by what Simon said. If you look at pure photonic devices like the glimmer glass MEMS device switch, and you compare that with that's our 410 switch in the lab, or 410 router, I should say, in our lab, but we use it mostly in switching mode. And such an old dinosaur up there at the right from your point of view, then there is approximately a factor of 10 difference in price. So what is the point? The cost of photonic equipment, so these, if you squeeze, you know, their marketing guy high enough, you get them somewhere below 1K port. He will love me for this remark. If you, 1 year ago, the price of L2 was pure L2, so, or these switches was about 5K per port. There are now even layer 2, pure layer 2 10 gigabit switches for around 1K per port for a 24 port switch. Forstena has just announced that a few months ago. And these layer 3 are still, you know, another order of magnitude bigger. What interestingly enough you didn't say is that if you look currently at the glyph and how some of those NRANs implemented that using HDXEs from Nortel, the interface cards and port prices of those devices are more, you know, ruining my model and in the L3 space. So I tell them that now and then, and they don't like that, but it is true. I mean, for that matter, you could exchange HDXEs just well for routers, in my opinion. And you should also include, of course, the DWDM lasers. They are also quite expensive, as you noted. However, if you look to the traffic patterns and the Class A, Class B, Class C, you notice that the Class C is usually point-to-point and medium to long-lasting. So it makes sense to try to map the Class A to layer 3 devices, Class B to layer 2, and Class C to layer 1. Give each packet in the network the service it needs, but no more, is kind of the point. So if you look at it, also in the equation goes the scale of the infrastructure. What you both talked about was your nationwide infrastructure. But there are, in my opinion, 3 scales. One scale is, let me start at the top, is the global scale, the transatlantic infrastructure. You will typically hire very expensive lambdas from somebody who put undersea cables there, and those will be sonnet framed. I mean, the chance that you yourself will put your own laser on their infrastructure is 0. So your interface in your router room will only go for 10 meters and then in the rack of the supplier of those lambdas. So then you don't have any long laser cost or whatever. Then you have the regional scale. You know, on the regional scale, so cross-continental, there are already many more lambdas available, and in the metro scale, 2 milliseconds, which is the size of the Netherlands or part of Switzerland, or, you know, you can have your own dark fiber networks, and that's now really growing. 4 years ago, I made this formula, the number of lambdas I expect NRANs to own. I estimated it being 200 times e to the power, fill in the current year, minus 2002, divided by the round trip time of the length of that lambda, and it's still pretty much fitting, I must say. But in the metro scale, you can use your own dark fiber network and use the photonic devices. However, the degrees of freedom for these different kinds of infrastructures are, of course, also different, and you need to fork that in. So our motto has been always, how low can you go? So you go from an endpoint to an endpoint for Class C. So I'm talking about Class C. You try to bring the traffic as low as possible, transport it as far as possible. You may have to switch to other technology levels to get through the next hop. You may come from a transatlantic sonnet circuit. You may want to pass for cross-border dark fibers through the Netherlands, so you need to go into a collar of SurfNet to the border and then cross the border and take the next hop. Some NRANs use layer 2 VPNs, some use pure color and do their decision and switching on that and so on. So you need these elevator services and open exchanges which can bring you from one layer to another layer. This is the glyph infrastructure. Most of you will know this picture. I will not spend too much time on this one. But these exchanges, which would bring you from one scale of networking, so from dark fiber to VPN to layer 2 VPN or to Sonnet or to really a routed interface, a routed network, you need these elevator services, so these exchanges like Netherlights, and they should give you, for different scales and different classes of users, different kinds of services. And that's given in this table. We have written an article on it. There's something supposed to happen which doesn't. Okay, then it doesn't. But now the arrows are there. So really crossing from one scale to another scale, or from going into certain types of aggregation is where the trick is. And basically, many of these tricks are currently already done, implicitly or explicitly. So we have made a model of an optical exchange as a black box, which can do these kind of changes to bring traffic from one to another layer. And if you want to see articles on it, email me or look on my homepage where I have pointers to them. So cases for circuits, and this is also, by the way, almost the last slide. I think cases for circuits are where one application wants to talk to another host, where the bandwidth need approaches that of the interface speed. Because believe me, if you have a routed infrastructure and you have a 10 gigabit connection between two major cities, and one application sends a stream of 8 or 9 gigabits through that, then your headroom is so little that you will get unpredictable results. Currently, LHC, Astro do that. And they got now currently their optical private networks or lambda-based networks. E-health and e-bioscience are around the corner. I said that also in my talk. LHC saw this light about 10 years ago. About 5 years ago, the astrophysics people came up with their EVLBI. And you see now the e-health and the e-bioscience coming around. It depends on the scale of the network and time factors of the application, what kind of circuit technology and control plane you will need. Do you need completely automated? Can you use some people setting it up, or do you really need to go to kind of telco way of SS7 like circuit setup through multiple domains? Inside the country, like what in the Netherlands is the philosophy behind SurfNet 6, is to copy the customer or the university interfaces to a central place and have only a few routers. So there are two big routers, one is backup of the other. You don't put routers at all the POPs, but you copy everybody's interface to a central place, and there you do your trick. And that saves you at least on the routers if you still want to do expensive routers. On circuits, the transport protocols can switch off congestion control, which usually ruins throughput. So, I mean, if you leave the congestion control on, that ruins throughput at these high-speed links. If I really look at it, the NRANs of today are the telcos of tomorrow. So, universities, you know what to do.
There you go first.
So do we have a question before?
Oh, he gave it just to me. What do you think about optical burst switching? It wasn't mentioned today.
Yeah, it's a pity. We had planned to have one panelist representing the optical burst switching alternative, but he couldn't come because of health problems. I really regret that because that would have been a very interesting sort of compromise between like the circuit switching and the packet switching people. I think optical burst switching is a very interesting technology. I cannot quite imagine how it would integrate into like a science network users landscape. That's why I regret so much that Mr. Mahoney couldn't come. But personally, I have high hopes into the optical people that they get optical packet switching. I mean, without the OEO conversion done when we need the capacity and the routers really start to become expensive.
Okay, next. Mike.
Since I have the mic, just one comment and one question. Just tomorrow, I mean, I thank all the speakers because I think they have provoked us in a very polite way. But you'd want to watch out for burstiness because we've already built this into the network. If you, number one, we segregate research and general internet traffic, and we devote lots of bandwidth to research traffic. We devote a lot of bandwidth to research traffic, so it is not surprising if on a large amount of bandwidth, a small number of users generate very bursty packets, whereas on the general internet, we get a lot of aggregation, and therefore it appears much smoother. If you compare, let us say, a high-end computing center where you need to build, a few hundred systems all at once, you have a large amount of data to transfer, and because there's a large amount of bandwidth devoted to that, it appears as a big spike. Whereas if you have millions of users downloading the latest Linux from your mirror server, it's going to be very smooth, but larger amounts of data. So you'd want to, as I say, we've built that into the infrastructure already, and don't be surprised if you observe this burstiness. My second question is a question really to Simon, and I wonder would he agree that another way of looking at this creative accounting is that the market is being segregated. What has been heretofore a fairly homogeneous research and education network, there's an incentive now to segment it and to tell people, yes, you need a wavelength. You're special. You need a wavelength. And if this is very, very loosely coupled, in fact, not coupled at all with any rigor, any discipline of economics, it is not surprising that people are going to take these things up. And that will justify your large capital investment, as you say, and the sales pitch that these things at the margin are very cheap.
Okay, first part of the question first. You have to keep in, it was not a presentation about monitoring. What I show was just the egress or ingress towards research and non-research part. But on the core backbone, they're both together. So actually you will see on your backbone the sum of the two, and the amount of traffic for both is almost the same. I agree there is a slightly less number of flows per second in the research environment, but the difference is not high. And in any case, what is even more interesting is that the application balance between the two is different. But again, in your core backbone, you have exactly the sum of the traffic. So that means even more burstiness if you want, because you sum two burstiness and they don't balance often. Okay, that's for the first part. Is it enough?
I would like also to make a remark here. So one of the big applications we cope with in the Netherlands is the VLBI. So from 12 different places in Europe sending multiple gigabit streams to one correlator in one place inside the Netherlands, not in Amsterdam, but in one of the remote POPs in the Netherlands actually. And if you look at it, if that would have needed to be done with using 10 gigabit interfaces in routers and so on, and then so that's one thing that would be cost inhibitive. And then if you would try to figure out how to set up the routing in a total all routing environment such that every stream goes through the right interface, through the right color, through the right interface, to the right cluster and correlator in Dwingelo, that traffic engineering is far from trivial. So in those special cases, you need to use these as scapegoats.
Yes, I mean, I would like to ask a question to Kes. He said that in his closing remarks something about university beware of NRENs, and if you could make that a little more, if you could elaborate on that a bit. But as an overall remark, let me say that in 1974 I did my PhD thesis on integrated packet and circuit switching. 1974. And we're talking about 56 kilobit trunks that were fantastic at the time, the ARPANET days and so forth. And what I heard today was about the same conclusions, or similar conclusions from what I heard, what is it, 79, many years anyway. But anyway, I would like really, Kasim, if you could elaborate on why why users and universities should be aware of NRENs.
Well, I mean, you see a kind of repeating history. I mean, I'm now about 10 years in this business, and I heard, of course, the guy with the same name as pre-name as I have, arguing about the telcos 5 years ago because they had a kind of monopoly and high prices and so on, and now they are becoming themselves. They got rid of the telco, but do all the telco services now themselves in some kind of way. So okay, if at some point the universities are now facing also the bills of that, and well, they get also different offers, so they could also try to think, well, maybe for some part of my network needs it may be nice to have my own dark fiber, so why not? So maybe this, but for the rest it was of course a little bit kidding.
May I would like to make another comment, is that first in my slides one of the conclusions I couldn't write was that in my opinion the standard production packet switched network has very good reasons to stay where it is, and it is still growing, first. Second, the panel is about circuit switching. Up to now, no one has shown any good reason to switch circuits. There are indeed very good reasons to provide circuits as a cost economical, technological facts and so on, but as I said, telescopes don't move, computing centers don't move, and so we have to keep in mind that the decision is whether to add a very thick layer to switch circuits or not. And I think we may live very well in a middle ground where we do have packet switching everywhere, we do create some switch circuits with maybe very low time to be, let's say, up and running, but not many, and it might satisfy our user requirements for a long time. So we have to be very careful when we talk about circuit switching. I know I'm one of the JR3 members, so I shouldn't say that, but nonetheless, this is why we are looking at that. But the time scale is different.
Yeah, of course, I cannot resist to react on that. It's very nice to be in academia and actually have a research function and an academic goal instead of running these networks. So that's one reason to do these things. But the other is, what we see coming is workflow-based e-science applications. So, sorry? Nothing? Yes, workflow-based e-science applications where applications need computer resources for data mining, big data stores, rendering clusters and tile displays or other visualization, high-end visualization resources. And in these workflows, going through such an application, going from data acquisition or whatever you do, storing, data mining and so on, at different stages you may need different topologies, and workflow-based topology steering of these kind of infrastructures may very well be one of the ways to give certain applications, and I agree not all, but certain applications who need that, the predictable network behavior they need. And clearly at iGrid, for example, some applications show that you really need to have kind of predictable network characteristics which pure Labdas can deliver. Please mind you, I'm not advocating here that we should get rid of all the packet networks. I mean, in the end, if you look to the applications just deal with IP or some form of IP, or they ruin the IP or TCP stack, but still they do some form of IP and run that over the Labdas. And of course, the class A, class B, you must keep on routed. I certainly agree with that one. Do you want to explain?
Well, I would like to ask a question, Jean-Marc Huzet from Juniper Networks, and would like to react to Simon's presentation. I have 2 points actually. The first one is more a clarification. Is there, you were comparing layer 3 switches.
I thought you would announce a new cost-effective 10 gig E layer 3 switching platform from Juniper.
Simon, you know me since a long time. I'm not doing this kind of things. Yes, first clarification. You were comparing layer 3 switching and routers, which is a very interesting topic. But is there any relationship with the packet-based network and switch-based network? I mean, I don't see the difference, the relationship between this topic, which is interesting, and I will come to my second point after that, with the topic of the panel.
Yeah, as I said, for me, my network is a routed network because it looks at network layer addresses, switches based on that. If you want to call that layer 3 switch because we use cheaper switches, then that's fine. But technically, for me, it's the same. Well, it's an interesting topic whether, like, the debate between layer 2 bridging networks, you know, like large bridge domains like other people do, and really rooted networks where you have routing protocols that use multiple paths and so on.
Okay,
so
but in your case, the switch root packet, right?
Oh, yeah, absolutely.
Okay, so we are talking about packet-based system and another packet-based system, right?
Yes, exactly. For example, the alternative that Case has presented, where you have one central router and the interfaces are just bridged to the customer.
Yes.
That would be
okay. That's another topic. So that was just a clarification. Now I come to my point, and I would first. A router are more expensive than switches. That's clear. The layer 3 switches I mentioned in general. What I want to say is the people that buy layer 3 switches to the routing or routers, in general, they have actually the same specifications. They don't put fancy things like unknown RFC that would justify a decision to buy a router. So that's why I think it's a really important topic, by the way, buying a layer 3 switch or buying a routers. And more, if you just follow an RFP specification table, you may probably be able to tick as many boxes with the advanced layer 3 switches and the routers. And people that buy an equipment, they don't buy a layer 3 switch or a router, they buy a system that do routing with multicast, IPv6, etc. So at the end, of course, then the price will make the difference and so. When people in their decision process do testing, something different happens sometimes. And I think that's the key thing I want to say is that it's really difficult to see the difference between a layer 3 switch and a router if you don't really try it. It's a bit like the pudding, where if you don't try it, you don't know the taste it has. And I think that's a really important message I would like to give to the community is making a decision to buy or to acquire, let's say, acquire a system in your network. It's really risky just to do it now only with some features request, because we don't end with the same systems. And I'm not talking about any vendor here, right? No. Really, I mean, there are vendors that do switch, other router, other both. So even for a router that do, a company that do both, it's a I think, important question as well. So I think we should do today much more testing activity when we are making a choice, because then we can really taste the pudding and know if it fits the requirement you have. And this is something that has a cost, of course, some human resource costs, but I think it's something that is more and more important today with the evolution of the technology.
So thanks for the question.
No, I mean, it's a reaction, as I said. It's a reaction.
Yeah. So
I want to also put something on the table. Sometimes I'm teasing my research group at the University of Amsterdam with the question, would we be sitting here or would we have this discussion if a router would cost $1, if a router port would cost $1? Yeah, well, it doesn't cost it in your case, I know. I mean, but if a router port would just cost $1, are there then other reasons why we would need circuits?
Yes, I mean, but
determination, traffic engineering, because you need to have huge flows which you want to put on each own color also.
Can we just do this in order? We've got a couple more people in the stack, so can we just...
I have mentioned that protocol unawareness of circuit switching is an important point sometimes in networks, and I don't agree completely to your conclusion. It was very good. No. But I would say it's important if you look about circuit switching, how far you go with your circuits. If they are end-to-end circuits, or if you end them at a certain level of your backbone. And then it makes really sense to have circuit switching, what I absolutely prefer, and then have packet switching to the end user. Makes sense. And to your presentation, which was very interesting, excuse me, Juniper, we like you, that's not against you. The thing I see here is, good, I finish very quickly. What do you think about quality of service in your network? Do you think you need it or not?
Okay, two answers, two short answers. The first one, I've not said that I don't want long circuits. This is what we are already doing. But there is a profound difference in the fact that you may create a single circuit because that's a good basic IP traffic engineering from Rome to even London, because it is the best peering place, and you create that on a circuit which is exploiting WDM at its best. And then, on top of it, creating a circuit switched networks or a packet switched networks. Don't mix the two things. They are completely different things. Okay, first part. Second part, quality of service. Yes, one of the missing characters discussed here was exactly quality of service. For example, a remote lab could be a good case candidate for circuit switching on demand to a very expensive microscope or something. Yes, why should you do that? Because you have not enough faith in your networks to provide you enough quality. Well, I still have to see someone demonstrating me, just because it's a panel and I'm provoking, that there is not enough quality. So, quality of service, fine. In Giant 2, in Giant 1, we even together provided an architecture of quality of service, which is up and running, and it's there. So, again, my talk was, let's quantify things, demonstrate things. I'm completely open to any demonstration of facts to discuss together. I'm open to a road towards circuits because I think they are very useful. We use circuits since the beginning. And now there are more and more use of a WDM circuits on a long path, which can actually completely change routing paths. But that's not circuit switching.
So since you asked me about the quality of service on my network, let me respond. Thank you. The cheap interfaces, yeah. The cheapness of the interfaces allows us to over-provision, as some people would say, or just decently provision backbone links, which is nice because we have several 10 gigabit links in our backbone, even redundant, and there's never even a gigabit worth of traffic load, like over daytime, if you look at 5-minute intervals. So the quality of service is fine, I would guess. It probably ends where there's a traffic shaping device at a customer side or a highly tuned firewall or intrusion detection system. What do I know? It's probably too good considered that what other people build into their networks to protect them from us and the rest of the internet. I think my quality of service is better than if Case would have, or I don't know, other people would have designed my network, because we have layer 3 optimized routing. We run OSPF on the entire backbone between all sites. Our routing metric is the delay of the link. We measure the links. The link delay for a Platinum Iridium 500 byte packet or something is used as the metric for the IGP, that is sort of the contrary of traffic engineering. We deliberately do the contrary of traffic engineering, so to make sure that the traffic always uses the shortest path. And why don't we need traffic engineering? Well, we know how to upgrade links if it's necessary, okay? And upgrading short paths is actually cheaper than upgrading long paths, or having excessive long path extra capacity. So yeah, I think my QoS is fine, but if customers disagree, then I'd be interested.
I sort of witnessed 2 full cycles of those circuit switched attempts, and it always goes like this. First, people start with PVCs, permanent circuits, that are, of course, as Mauro mentioned, labor intensive, but we are told that, okay, after all this technology matures, it will be much better. But as soon as people start implementing those improvements like SVCs, then it all becomes terribly complex and it all breaks down, and these people move to the next cycle. Just this happened like that with X25, this happened with ATM, and I'm not an expert in that area, but as far as I understand it, in this optical technology, we are in a phase of some kind of soft PVC, something like that maybe. So I don't really believe this will ever become less labor intensive. So from my point of view, if we have few power users who can be satisfied with something like PVCs, permanent networks, okay, that's fine. But if we want to compare comparable things, and if the question is formulated as whether packet or circuit switched networking will prevail, so for me this has been already answered by the historian. That's clear.
We have another question here. In fact, we have about 4 in the stack, so and I'm going to go into buffer overflow to get any more.
Hello, I'm Dimitris from GeoNet. So we had a comparison in terms of cost for running a network of a high capacity network. Those costs were only the capex. So we haven't yet put into the formula the opex, which is what normally businessmen do when they would like to run a network, because you need something to operate the network. So OPEX, let's see how OPEX gets into the formula. If you have networks which have no cleverness, then OPEX gets higher and higher. In some cases, if you like to do failure localization and trace errors, you need nice functionalities like the good old ICMP functionalities and traceroute, which are not already there. And in your networks, where you have Ethernet end-to-end, and with some kind of Ethernet over MPLS, you need some guys working for transforming the good old ICMP to MPLS ICMP, and then to Ethernet ICMP, which is not yet ready there, standardized. So it seems like we need to estimate the OPEX in order to have a fair comparison of what is cheap and not. Of course, in our case, I mean, in our NRNs, the size matters, of course. And we might have only 4 clients or 4 experiments, and then OPEX is limited. But I think we cannot generalize based on that.
Well, I agree that the complexity of setting up these circuits is currently high, and that certainly a lot of work needs to be done by both Mauro and groups like mine and others to fill in puzzles. And we should get at some point where we really virtualize these things in the sense of hiding away all the complexity. So there is a lot what needs to be done, but also mind you that I think the switch circuit or static circuit needing applications where the C-class, which are at the far end, are as you say, 4 in your network, or some 10 here, or some 5 there. So currently scalability there shouldn't be a big issue, although I know and I agree that currently you need almost half a person or so to just do the circuit switching business. And certainly around supercomputing, you know, that are the highlights where all this is coming together.
Yeah, the interesting question is, of course, do you really believe that this will somehow generalize, that there will be more and more of these people who have like well-known in advance bandwidth needs and well-defined workflows and so? Because I know there are some people like, I don't know, Jim Gray from Microsoft, for example, or the expert panel who worked on this 2020 science expertise. Do you? No, that's interesting, slightly large report. We have different opinions on where the computational science is heading or should be heading. And personally, to come back to the response I still owe to Dave about the user segmentation, yeah, I have exactly the same impression. These research network operators try to segment their user community and slightly maybe overemphasize these needs of the applications such as LHC because they're easy to sell. And yeah, I think that should be taken into account. As I said, I'm just a small network. We managed to somehow get rid of our high performance users. Like we placed the Géant connection in Geneva. That has a reason, okay, that we didn't put that in to Zurich. That would have made things a little bit more difficult for like supporting CERN. And it's also true that we are funded by our connected organizations, and we have like continuous funding and some capital on the bank, and that makes the situation completely different for us, as opposed to a network who has to go every n years, like typically, I don't know, n between 3 and 6 or so, and request a huge amount of money for building a new network as a project. Like our network is continuously being replaced, so we never have to do that. But many other networks work that way. Géant is an example, many NRANs too. Every 5 years you have to come up with the new big thing. We don't have to do that. And the new big thing, well, it turns out it's always circuit switch networks for some very important users. And then, well, people forget.
My question is actually related to the question of the previous speaker of the Apex versus OPEX. Kees did talk about the cost of devices. Mauro, you did talk a little on the cost of the operation itself. Actually, there's an RFC out for 4 years ago, 3439, in which there's a section on exactly this topic, packet switching versus circuit switching. The conclusion, by the way, is that they say that packet switching of circuit switching might be quite interesting, so you might read it. But one of the conclusions also in that RFC is that there's no direct relation, or at least they could not find one in literature, between the complexity of your network and really the OPEX or the APEX. And it seems obvious to me that the complexity on a data plane leads to complex devices, and thus high cost of buying those devices, high APEX. And complexity in the control plane, for example, for circuit switch networks, leads to a high operational cost. Now my question is, do you think that that operational cost will decrease with all the new control planes that are coming out, GMPLS for example? And for the network operators in this room, what's more important to you, the APEX or the OPEX?
Okay, a small and fast answer because it's time, about the operational expenses. One of the facts that was hidden here is that our network are not the same as 10 years ago. They are roughly 10 times larger. So In any case, you have to provision at least 10, not 10 times, but a certain factor of increase in operational expenditure just to the sheer increase of the size of a network. What I try to show you very, very briefly is that if you increase the network according to the standard internet principle, that increase is what you can say natural growth. You can't avoid that. Then there are two additional reasons to increase the operational expenses. One is new services. New services bring new functionalities, require new functionalities, and you have to have new people to put that functionalities in towards the users. Whether or not to choose a new service, that is up to us, but essentially up to now, new services can be even multicast, and we added a person for multicast. It could be IPv6, and we need to have experts on IPv6. What I have as a feeling, because I would try to quantize that not just for the NRN, GAR NRN, but also for others, is that while the increase for multicast or for IPv6 is linear, is what you expect, if you go to MPLS, then there is a quantum leap. It's not one more, it's 2 or 3 more, and then it's not enough. And then, for those very high related technology to end-to-end things and state-aware technologies, is not just on you. You have to rely on others, because it's a connection-oriented thing. And the network has state. That state should be common to others. You have to phone others. You have to use a control plane to signal things. The signaling protocols are complex. Well, my feeling is that this is the quantum leap. The network is more complex. I try to show you that for the bulk of it, you don't really need that complexity. You can live happily with much simpler solutions. One of the complexities is that you have to monitor the network. But then you have to decide what to do. If you monitor a pure packet switched networks, GN2 is developing a very good distributed system. You have very good tools, SNMP. You can really debug things. You can oblige optical vendors to add SNMP to their switches. So you naturally add the optical switches to your MRTG graphs, and that's it. If you add MPLS and a very complex control plane, then that's not the story. And I bet that you need at least not 1, but 2 to 3 times more effort. Personal feeling, this is a panel, so.
Okay, we've got one more question here at the front, one more question there at the back. Then I'm going to call it quits because there are several buffs starting around now. So 2 more questions. Okay.
Perhaps mine is not a really question, but talking as a small NRN, perhaps a little bit like Switzerland, I'm Victor Rice from HANet. I think we are doing switching network. We have a switching network in HANet, not a circuit switch network. We have an Ethernet switch network at the basis. I think the reason for that is not because we have big, large users who need point-to-point links like the EVLBI. I think they don't exist in Ireland in some way. Not because they are in another country like you could do, but they don't exist yet. But where are these point-to-point links needed is within institutes. So institutes are now going to buy from HANet a point-to-point link to connect their campuses together. And almost 50% of the point-to-point links we are making are for this kind of goal. So nothing to do with big users. No, just because we have this dark fiber infrastructure now and we have a switched Ethernet service there, we can provide these links, people with point-to-point links. That's one example. For the other one is that we can easily now connect our IP router, make it smaller, make it in a central location, and then doing this copying, we already do that. So that's another thing. And we see that there are researchers, I see you, that there are researchers who want to have CWDM circuits, not so real lambdas. Yeah, we can also now provide that not as a production service, but as a pilot service. So by having this dark fiber and these servers, we are easier and more flexible in providing new services, like a telco, and hopefully as a proper telco. Yeah.
Thank you for being so brief, Victor.
Yeah, same holds for SurfNet. They also deliver these optical private networks, optical private networks, virtual private networks, OVPNs.
Okay, just I want to make the last comment, if I may. I see that, talking about circuit and packet switching so far has been concentrated in a very specific thing, which is a single domain network. I think that the main challenge that we're facing as an end-to-end community is not a single domain issue. There you can do whatever you want. I mean, you can use all kinds of proprietary solutions, all kinds of complexity. It's not the main point. The main point is that in order to connect my cluster to another cluster in the United States or whatever, you need to go through 4 or 5 different domains that may use completely different technologies. Some of them may use packet switching, what do you call it, PIP, what is a PIP? Premium IP, yes, premium IP. Others can use MPLS, others can use Ethernet over MPLS, others can use whatever. So the main thing is, in my view, is to be able, for this kind of applications, to be able to establish end-to-end paths across multiple domains in a technology agnostic way. And by that I mean that we need provisioning schemes that are, first of all, modular, that are at the service level that talks something standard with the lower levels that we don't know exactly what they are. They could be whatever, and that's web services, that are modular, so whatever we do right now, we just can throw it away, and whenever industry is going to come up with the standard solution, we can replace it very easily. So this is the way that I see, I mean, this I see as the main challenge. So JRA3, Mauro, is, I believe, going the right way because it takes this modular approach, it takes this web service kind of interfacing to whatever box manages the lower domains. And I think technology agnostic protocols definitely needed in there because otherwise you cannot set up end-to-end paths across domains that do not talk the same control plane. I mean, I use that all the time. There are only, in my experience, 2 NNI control protocols that have succeeded so far. One of them is from the circuit switch domain, and that's S7, and the other one is from the packet switch domain, that's BGP. I haven't seen anything else working so far. I may be a bit, not seen far away, but so far I haven't seen, for instance, multi-domain MPLS. I haven't seen all these ATM, PNNI, brilliant ideas. I haven't seen anything of that stuff working. I've seen only those 2 things. That's the reason why I support fully what JRA3 is doing, trying to build a standards-based, technology-agnostic end-to-end provisioning scheme.
So you think you can pull this, or JRA3 can pull this off and succeed in building the 3rd interdomain signaling protocol that works? Okay, I mean, if you look at the alternatives, SS7 is probably not good enough because it only lets you signal like 64 kilobit channels. But BGP is like, for me, it's, I mean, it has its problems, but I mean, there is this way we connect disparate networks, and it's called internetworking. So we use IP. Wouldn't it just be great if the IP networks would be good enough? Then we just interconnect them, and we have we can support all these applications that want to do multi-domain connections. They use end-to-end connections.
I could be very happy with BGP, with whatever you want to call it. Yes, but reality is not like that. Reality is that you do have to deal with what you call it, with layer 2 technologies, with layer 1 technologies. You have to deal with all sorts of technologies, and those have to stitch one to another. And this is reality. I'm not talking about what the ideal world should be. The ideal world could be probably everything IP. No problem with that. But we're not living in an ideal world. We're living in something that, that we have to get several technologies to be stitched together to create an end-to-end path.
So for researchers, this is of course an ideal world to be working in because there are so many questions open still. The AAA question is one. So you are right. There's really a lot which needs to be researched here in terms of this signaling.
Okay, and with that end of that lively session, can we thank the speakers and the panelists? and thanks you lot for coming along and making it fun. It's been good. Thanks.